Hello viewers, thanks for taking the time to watch my video. My name is Anthony Palma, and today I'm going to be discussing Higgs boson and the Higgs field. So, for starters, I'm going to give you a brief historical overview of Higgs boson so you can scale how far we've come since the theory was originally hypothesized. So, the original conceptualization of the theory occurred in 1964 by a group of physicists and scientists, and that included such people as Brout, Englert, Higgs, Grolnick, Hagen, and Kibble. Since then, the most dramatic events to support the theory have occurred in the last decade. So originally in 2012, a new particle was finally discovered, and it had a mass of 125 giga-electron volts per speed of light squared. And that was discovered at the Large Hadron Collider, and it wasn't until March of 2013 that it was actually confirmed as Higgs boson. So, for starters, where does Higgs boson and the Higgs field originate from in physics? So over the past several years, physicists have created a model which is used to explain the current understanding for particles and forces which exist in nature. But in order for this model to work properly, a hypothetical quantum field is required to exist, which has been named the Higgs field. In this model, identified as the standard model, it is identified that the Higgs field is what actually causes particles to have mass. And this is due to an interaction with this field. So in this model, which we've identified as the standard model, it's determined that the Higgs field is actually what's causing the particles to have mass, and that's due to the interactions with this Higgs field. Now, this field is known to act equally all throughout the universe and leads to the following reasoning for why some particles have mass and some don't. So the understanding is that massless particles such as photons do not interact with this Higgs field, and particles with mass such as W and Z bosons do get bogged down because they do interact with this field. So the next thing to consider is that even though this field exists, why is there a Higgs boson particle? For this, we must consider the quantum theory of wave-particle duality. Now, getting into too much detail of wave-particle duality is out of the scope of this particular video, but I'll give you a brief explanation on what that actually means. So, wave-particle duality is a concept which is derived from quantum mechanics. What this concept states is that every particle may be partly described not only in terms of particles, but also in terms of waves. So this is due to the fact that particles or waves cannot fully describe the behavior of quantum scale objects. So now a bit of a look at the elementary particles. This diagram is just an indication of several of them, which exist in the standard model. An elementary particle is one which is not composed of any other particles. They are the most basic constituents of matter. The four different types here are outlined. So here we have in orange quarks, and then in the green we have leptons. Blue is the bosons, and then finally the purple is the Higgs boson, which we're covering today. So a bit more about the standard model. So as was mentioned, this Higgs boson field and particle are required as a part of the standard model. So the standard model is a name that was given to a 1970s theory of fundamental particles and the way that they interact. This theory allows for three of the four fundamental forces to be described, excluding gravity. So the other forces, as can be seen, are the electromagnetic, weak, and strong interactions. These different forces can be seen in the image on the screen. So the strong force is an attractive force between subatomic particles, such as the protons and neutrons, which allows for the atomic nucleus to be held together. So next, the weak force. This force is stronger than gravity, but only effective at short distances. It's noticeable at the subatomic level and vital in its role of powering stars and creating elements. This force is also responsible for much of the natural radiation that exists. The electromagnetic force has an infinite range, such as gravity does, but is a much stronger force. And then the fourth force seen in the model is one that we're much more familiar with. This is Newton's gravitational force. This is the weakest force that exists, but has an infinite range. This is the one force which cannot be explained in the standard model, meaning there is still work to be done with this model. So here's a look at the Large Hadron Collider. This is the largest and most powerful particle accelerator in the world, and this is where the experimentation occurred to discover the Higgs boson particle. This machine is a 27-kilometer long underground machine which exists between the borders of France and Switzerland. So the way this tunnel works is that beams of proton particles are accelerated to extremely high speeds, close to the speed of light, and then slammed together into one another. Then what happens, once they collide, the results are recorded. And so what's impressive about this is that the energy densities closely resemble the Big Bang and are closely resembling the Big Bang are able to be simulated. So now we have a look at what happens after the collision. So after this occurs between the two particles, there's tracks of subatomic particles created, which can be resembled in the image on the screen. And then scientists study these tracks. So after the collision, many subatomic particles become exposed, and on July 4th, 2012, it allowed for a new particle to be discovered, as was mentioned. It was later determined to be the Higgs boson particle. So that ended up actually resulting in Francois Englert and Peter Higgs winning the Nobel Prize in 2013. So it's said that a Higgs boson particle will only be created 1 out of 10 billion collision, and it decays very quickly, so it's impossible to detect it directly. So in order to determine if it does exist, the decay products were registered, and the process was reconstructed, and then the data was analyzed, such as the decay rates, the spin, and the parity, and that's what allowed it to be confirmed as the Higgs boson particle. So let's conclude the presentation for today. Thanks for taking the time to watch my video, and tuning out till next time. Thank you.